Logits are the raw outputs generated by a model before applying any activation function, such as Sigmoid or softmax functions. These values are unbounded, meaning they can be positive, negative, or zero. Logits represent the model's unnormalized confidence scores for assigning an input to different classes. In a classification problem, especially in multi-class classification, the model produces a set of logits, one for each class. These logits indicate the model's relative confidence in each class without being normalized into probabilities. Let's consider a 5-class classification problem. We can emulate such raw model output with the NumPy random. Let's first of all import NumPy as the NumPy. And to ensure reproducibility, let's set up the random seed. We need to call NumPy random seed and install, for example, 42. As the step number 2, let's create a logits variable and call NumPy random dot randn, where we'll generate normally distributed values. Let's say 5 values, and then we can print them. And it looks like this. These are the raw outputs. To convert them into probabilities, you can apply the Sigmoid function. For multi-class classification, we typically use the softmax function rather than the Sigmoid function to convert logits to probabilities. But just for simplicity, I'll use the Sigmoid function. These logits represent the raw unnormalized scores assigned by the model to each of the classes. They can take any value, positive, negative, or zero. Let's take a look inside the linear layer. And the linear layer performs a key operation, a linear transformation. This is represented as the argument of the sigmoid function, where Wi transpose are the layer's weights and Bi represents the biases. The term Wi transpose times x plus Bi applies a matrix multiplication, weights times the input, and adds the biases. We can simulate this step with the NumPy. We can generate the random matrix of the weights. We can create absolutely random input x, but for the weights it must be 5 times 5. We generate a matrix of the weights, and let's create a bias vector, NumPy once and 5 items inside this vector. So, and to generate one step inside our model, inside this linear layer, we can create a variable x1, and we need to multiply our matrix weights W dot product with the input plus bias, and let's print the result. And here we go. You can see that it works fine. We have rough model outputs, and it's pretty similar to our previous result, but in the previous result we generated 5 random values, and here we just have a small simulation of this process. To make these logits interpretable as probabilities for each class, we use an activation function. In this case, it's the sigmoid function, and the sigmoid maps these raw values into a range between 0 and 1. And the sigmoid function defined as 1 over the 1 plus e to the negative x power. But it's very important to track the sigmoid and the derivative of the sigmoid function. And it highlights a key property of the sigmoid function. Its derivative can be expressed directly in terms of the function itself. If you wanted to check, if you wanted to see how we derive this derivative formula, you can check my blog where I just did this step by step. And now let's implement the sigmoid function. We need to create a class sigmoid. Then I wanted to follow approximately the same API as in PyTorch. Let's create a method forward. And we have self and x as the input of our sigmoid function. We can mark it as NumPy and the array, and we will return NumPy and the array. Okay, good. So then we have this formula, and we can implement this just by the same way. Yeah, we just need to return 1 over 1 plus numpy.exp to the negative x power. Yeah, it looks nice, and let's define one more method, backward. And we have self and also input x. I think that we can copy and paste it right over here. Okay, good. Then let's define a variable sigmoid. We can call self.forward and put x as the parameter. So then we know that we can return the sigmoid times the 1 minus the sigmoid. Okay, it looks almost perfect. Yeah, we have the same API. Yeah, I don't know, the same notation. Yeah, we have the same sigmoid times 1 minus the sigmoid. Yeah, it's quite cool. Let's leave it as is. And I have a plot of sigmoid and derivative of the sigmoid. So we create an instance of the sigmoid class, generate an array of values x as the input. Then we call the sigmoid with this input with forward method and with the backward method, and build two subplots with the sigmoid and with the derivative of the sigmoid. For the sigmoid, visualize x against the sigmoid values, and for the derivative we use x against the sigmoid derivatives. The sigmoid function maps input values to an output range between 0 and 1. For large negative values, the sigmoid output approaches to 0. For large positive values, the sigmoid output approaches 1. And this right graph shows the derivative of the sigmoid function. The peak at 0 equals at x equals 0 highlights the point of maximum sensitivity. Any small changes towards 1 or towards -1 just change the behavior of the output completely. Yeah, because this is the region 0.5 where we can't define for sure, yeah, is it positive class or negative. At the tails, you can see that the derivative diminishes, leading to the vanishing gradient problems. And in deep neural networks, it can cause the vanishing gradient problems. Yeah, the sigmoid function is not a good choice as the intermediate activation function between layers. And now let's use the sigmoid function to transform the simulated logits into probabilities. Let's copy this layer code, and also let's copy the sigmoid. Yeah, and we create an instance of the sigmoid right over here, and instead of the raw logit outputs, let's call sigmoid forward and put our x1 right over here. And here we go. The output shows the normalized probabilities for each class. These probabilities are easy to interpret and directly usable for classification tasks. Yeah, you can see that right now our probabilities just shows us some result. Yeah, we can put a threshold, let's say 0.5, and then classify our class is negative or positive without any problems. And I have one more simulation for you. It's Logits versus the probabilities. From one side we have a raw model output, from the other hand we have Sigmoid probabilities. And we can add more classes, but I think that we can stop at like number 5. And it's pretty obvious that from one side, when we have a raw model output or the logits, it's absolutely unuseful. Yeah, we can't decide for sure what is the output our model predicts. But when we have this sigmoid probabilities, it's just completely useful because it's already meaningful probabilities ready for decision making. You can see that in our example, first bar it's 0.95 and we converted to probability 0.72, very high probability. Then we have 0.65 bar and we converted approximately to the same probability, 0.65. And for the model output negative 0.31, we converted to a little bit lower probability, 0.42. And this last probability is very interesting. Yeah, we have negative 0.77 and we converted into a low probability, yeah, 0.31. This transformation shows us map the model's raw output into something meaningful that we can use for our application.